Hello and welcome to our second beam flexure test. This is part 2, the aluminum beam for our strength and material lab. And once again, make sure you have a clean notebook sheet, something that you can take notes, both for taking material data results as well as measurements of the sample. So here's our aluminum beam. Now what we see a little bit different is on the right side there, we're actually going to be imparting a deformation, and we have a way to measure how much deformation that is. And on the left, again, we have fixity, but as we get a little closer, you can see the fixity method is a little different, and we still have a strain gauge up on the top. Now, I'm going to put a ruler so that we can measure the length again, and I have this second ruler that attaches or pushes right against the tip of our device there so we can line things up perfectly. So pause the video and take a reading where the displacement is imposed, and then pause again to get the center line of our strain gauge from the fixed end of the beam. So here's our system. We still need to get the width, so we'll take our 3 measurements again of the width, and then we also are going to need to get the thickness, which we can only do at the front end of the beam because our measuring tool does not fit between the beam and our support here. But you can see from our 3 measurements, just like the steel beam, we're basically at 1/8 of an inch, 0.125 inches, so you have 0.122. All right, so here's our system again, and again, this time we're imparting deformation so that we have a place to start. We actually are going to forward our device until we can actually have the, it's contact. So we want to push to contact, and it looks like we get to about 1.04, so we see the 4 lining up on the horizontal axis, lining up with the vertical axis. So that's going to be our reference for each rotation. Now on that vertical axis, we have about 1 inch showing there, and it's divided into 40 ticks, so each tick is representing 0.025 inches. We want to impart 1.1 inches of deformation, so we're going to need to do 4 rotations before we do a reading. So each rotation is 0.025 inches. So here's our 4th rotation, lining up that 4 tick mark. So we have 152 microns. That's what the computer up there is showing, is 152 microns. Remember, times 10 to the minus 6 is how you get the real strain. Okay, here's our 3rd rotation. Let's watch for linearity. We doubled the deformation. Do we double the strain? So now we're at 0.2 deformation, 0.2 inches. And we're going to do 4 more rotations to add a 3rd 0.1 inches. So let's see what that gets us. Again, watch for the linearity. If you're increasing the deformation by an equivalent amount, you should be increasing the strain by an equivalent amount, because we should be increasing the force. The force results in a moment, the moment results in a stress, the stress results in a strain. All right, we're going to, just like the steel beam, back this off slowly and go ahead and take readings just to reassure yourself that we're seeing a linearly elastic behavior. So there we go, now at 0.2, and we had 298. And we had 306 microns on the way as we loaded it. So that's when you get out to the 6th decimal point, that's actually pretty good, right? Here we are at 0.1 inches and 145, and then we'll go ahead and unload it back to 0. Now I'm going to assume that some of you were very much focused on the dial or the actual strain readings, and so you didn't see how much the beam actually moved. So now that we see that we've gone to 0, let's just play that again at super high speed. So this is 1,200 times faster than it went before, but you can really see the beam moving. All right, so here we are. Here's our final system. Now, as you read the lab report, you know that you've been given a formula where you can take and relate a load that has to be applied to get the free end of a cantilevered beam deflecting versus the actual deflected amount. So this time we know the deflected amount, so we can back calculate the load that would have had to have been applied. Of course, we can then draw a shear moment diagram based on that load and get the moment applied back at the strain gauge. If we know the moment back at the strain gauge, you all can calculate the maximum stress at the top of the beam, right, at the outer fiber of bending, and then that's your theoretical stress based on the theoretical formulas, but of course you can also get the strain at that location because we measured it. We have Hooke's law, we know the modulus elasticity, so you can also get the experimental stress that's going to be occurring there, and you want to be able to compare how the two values compare. All right, so thanks for watching. Now you want to make sure that you have all your correct measurements. You could compare with a classmate to see what values did you actually think were important, what did you measure, and start to do your analytical analysis. Have fun!